Okay, if I fill the cylinder with Coke, what you can see now is that I obviously have a lot of bubbles in the fluid, and the measurement is ambiguous. I can't see, if I just look at the brown fluid right now, you can see that it's changing because liquid which is trapped up in the bubbles is slowly dropping down into the solid part of the fluid, or total part of the fluid. This is an example of what we call a multi-phase problem, where I have some of the fluid is liquid, but some of the fluid that I'm trying to measure was also in there as gas, okay? And it becomes difficult to make that kind of measurement. Fuel and water are the two most important quantities that are monitored on board the ship. However, it's interesting to note that there are no fuel gauges or water gauges here on the bridge. Those quantities are actually monitored below decks. I've come 2 levels below the bridge to the top of the fuel tanks to show you how fuel is actually measured on board the Albatross. The way it's done is much like the way you would measure the oil in your car. What we actually do is come to several of these what are called sounding ports to dip the tanks. These are 2 for the forward fuel tanks, the port and starboard tanks. So if I just show you, what I do here is take this tape measure with a weight on it and put it down into the sounding port all the way down into the tank. When I reel it up, what I'd see is that the fluid would have wet the tape measure at some point. And there are sounding tables which convert the height of the fluid to the amount of fuel that are actually in the tank. There are different sounding tables for each tank because their geometries are different. We're now 4 levels below the bridge in the lower engine room, and I've come here to show you an example of a very simple level gauge. Behind this wall up here is the hydraulic fluid storage tank on the ship, and this is a simple sight level gauge. It's simply connected into the tank at the bottom and top of the tank, and you can see that the level of fluid in the tank is monitored right here. So in fact, the level of fluid in the tank is right back behind us here, so that the crew can monitor the level of hydraulic oil. Now, this gauge isn't calibrated, and in fact it's not necessary. They've just put some marks on here to know where the normal oil level should be. You can also measure the quantity of fluid in a tank using a simple float system. This is a simple fuel gauge where this cork float rises up and down with the level of fuel in the tank and is displayed on a calibrated gauge here. Actually, this is an uncalibrated gauge because it doesn't have any numbers on it. The same technique can be used in a very simple closed-loop control system to maintain the level of fluid in a tank. The float is connected to a switch. If the float goes too low, that switch opens and allows more fluid to come into the tank. If it gets high enough, it shuts off the switch. And you can probably actually see this in the toilet in a bathroom in your house. One electrical technique that we use to measure fluid quantity is a capacitive technique. Now, the capacitance between 2 electrodes is dependent both on the dimensions of the electrodes, both their length, their width, and their separation, and what's in between the 2 electrodes. So, for example, if we have air between the 2 electrodes, it will have 1 capacitance. If we put a material like fuel or water between the electrodes with a different dielectric permeativity, that will change the capacitance between the 2 plates. We can use this principle by putting those plates down into a fuel tank or some other liquid tank. And if we know the dielectric permeativity of the liquid, as the tank fills, the capacitance of the gauge will change. Now, this actually turns out to be a very nice technique for fuel gauges, particularly in aircraft, because the change in permeativity with temperature is about the same as the change in density of the fuel with temperature. So this can be calibrated to effectively be a mass gauge. Now, we run into a little bit of a problem with aircraft fuel tanks because the fuel is normally stored in the wings, and as you go out to the tip of the wing, the fuel tank gets smaller. And the way we actually adjust for this is we put several capacitive gauges in the tank, and we adjust their dimension so they're effectively weighted by the dimension of the tank at the measurement location. So essentially we've calibrated out that non-uniform tank geometry. Another technique which is used for fluid quantity gauging is an acoustic technique, which is similar to the sonar and depth finder on the ship here. Now if you look at the display from this depth finder, there's actually two scales here. One is a very large scale and one's a small scale. If we look at the bottom, what you're actually seeing are the echoes from the bottom of the harbor, which are about 3 meters below us. And in fact, you can also use this to find fish. You'll sometimes reflect off the fish. The way this works is an acoustic transducer in the bottom of the ship transmits a pulse down into the water. It travels to the bottom of the harbor and is bounced off the mud at the bottom of the harbor, reflects back and is picked up by another transducer in the bottom of the ship. By knowing the time between when we transmitted the original ping and when we received the return echo, we can infer the depth of the bottom of the harbor if we know the speed of sound in water. The distance is essentially the round-trip time times the speed of sound divided by 2 because it was the out and return time. We can use the same technique. We would put a transducer in the bottom of the tank and have it transmit the acoustic wave up into the fluid, and the wave would be reflected from the air-fluid interface and again be returned to the transducer at the bottom of the tank. By again knowing the round-trip time and the speed of sound in this fluid, we can then figure out the depth of the fluid. Now this has a little bit of a problem in that the speed of sound depends on the temperature of the fluid, so we may have to also monitor the temperature of the fluid. We can use the same technique in sort of a different way if we were to put an ultrasonic or acoustic transducer on the top of the tank, reflect and send the signal from the air, reflect again off the air-liquid interface, and use a pickup on the top of the tank. This has the advantage that you can use it for materials where the acoustic wave may not propagate. So, for example, you could use it for grain or for sand. And we looked at one of these transducers when we were at the Omega Engineering Labs. I have here an example of an ultrasonic level sensor. What I have here is the transducer, which then sends a wave down into a tank. And normally this is used in a very large tank. The ultrasonic wave reflects off of the surface of the fluid or grain or whatever material you have in the tank and is reflected back to the transducer, which picks up the return pulse. By knowing the time it takes the pulse to go down to the free surface and back, you can figure out how much fluid you have in the system. There are many different techniques that can be used to measure fluid flow, and I'd like to first talk about those techniques which are commonly used in constrained systems such as pipes. Now, in a constrained system, you don't need to know about the direction of flow. All you really need to know is the magnitude. One common technique that's used in fluid delivery systems, such as gas pumps or this oil pump here in the engine room of the Albatross, is a positive displacement flow meter. And there's a positive displacement flow meter right down here in this system. Now, conceptually, the way a positive displacement flow meter works is to count fixed volumes of fluid that go through the flow meter. So you can think of it as filling up this bucket, pouring it out, filling it up again. If you know the volume of the bucket and you know the number of times you filled it up, you know the total flow that's gone through the system. Now, actually, the way this one works is that flow goes through this meter. As the flow goes through, the fluid actually, in fixed volumes, pushes through a mechanism, effectively a cam, and as it pushes through, it turns the mechanism up in the gauge here, and you actually get a count of the number of fixed volumes that have gone through the system. This is a very nice technique in that it's a mechanical technique. However, it has the disadvantage that there's a fairly high pressure drop across the the meter. So as a result,